In Module 6, Lesson 11, we'll describe distributions using the mean and the mean absolute deviation, much like we did in the past lesson. In Lesson 10, a data distribution was characterized mainly by its center, or the mean, and its variability, the mean absolute deviation. How these measures help us make a decision often depends on the context of the situation. For example, suppose that two classes of students took the same test, and their grades, based on 100 points, are shown in these following dot plots. The mean score for each distribution is 79 points. Would you rather be in Class A or Class B if you had a score of 79? Notice in Class A your 79 would be right here. In Class B your 79 would be right here. Looking at the dot plots, which class has the greater mean absolute deviation? And explain that without actually calculating the mean absolute deviation. Well, recall that the mean absolute deviation is the average of all of the absolute values of the deviations for these values from the mean. So looking at our Class A scores, '60 is quite a bit further away from the mean than in the Class B scores, in which 77 has got to be much closer to the mean, which of course is 79. If Liz had one of the highest scores in her class, in which class would she rather be? Well, if she has one of the highest scores, Class A has higher scores in general than Class B. The highest score in Class B is 81. That would mean that Liz would be around 88, 89. So of course she would rather be in Class B. If Logan scored below average, in which class would he rather be? Well, again, looking at our scores, put the wrong thing there. Looking at our scores, we notice very little variability in Class B. So if Logan scored below average, he would want to be in Class B because the lowest scores in Class B are 77, 76, I guess. Now, if your little brother asks you to replace the battery in his favorite remote control car, and the car is constructed so that it is difficult to replace its battery, you would want to get a battery that will last long enough that you don't have to keep on taking it apart and replacing the batteries. Your research of the lifetimes in hours of two different battery brands, A and B, shows the data in the table for 20 batteries from each brand. To help you decide which battery to purchase, start by drawing a dot plot for each brand. And you can see in our dot plot the brand A has a lot of variability in the length that each battery has its life, where brand B is quite dependable, 18 to 22 hours for each one. Next, we're asked to find the mean battery life for each brand and compare them. Remember, to find the mean, we add together all of the data and then divide by the number of pieces of data that we have, which is 20. So we add these all up in brand A, divide by 20, and we find that the mean is 20 hours. And then for brand B, we do the same thing. Add them up, divide by 20, and we also find that the mean is 20 hours. So looking at the variability of each data set in its dot plot, what is one reason that you would choose brand A, and then what is one reason you would choose brand B? Well, looking at brand A, there's a possibility that the battery may last 27 hours. Whereas brand B is more dependable and should definitely last at least 18 hours. You've been comparing distributions that have the same mean but different variability. As you've seen, deciding whether large variability or small variability is best depends on the context and on what is being asked. For example, in exercise 2, Liz preferred to be in the distribution with more variability because she had one of the highest scores in the class. Thus, her score would have been higher had she been in Class A than had she been in Class B. Logan, on the other hand, preferred the class with lesser variability, which was Class B, since his score was below average. If two data distributions have different means, how does a measure of variability play a part in making decisions? Suppose you wanted to answer the following question. Are field crickets better predictors of atmospheric temperature than katydids are? Both species of insect make chirping sounds by rubbing their front wings together. The following data are the number of chirps per minute for 10 insects each. All the data were taken on the same evening at the same time. So we'll draw dot plots for these two data distributions using the same scale, going from 30 to 70, and then see what we can tell visually from those dot plots. So visually, we can see that their distributions seem to have a very similar pattern, even though katydids have more chirps per minute. That doesn't necessarily mean that they're not communicating the same information as crickets. Next, we'll calculate the mean and the mean absolute distribution or deviation for each distribution. So the mean for crickets is 35 chirps per minute with a mean absolute deviation of 1.2 chirps per minute. And katydids, the mean is 64 chirps per minute with a mean absolute deviation of 1.6 chirps per minute. The outside temperature, T, can be predicted by counting the number of chirps made by these insects. For crickets, T is found by adding 40 to its mean number of chirps per minute. So what value of T is being predicted by the crickets? So we would take the mean, which is 35, and add 40. And that would give us 75 degrees, the predicted temperature. For katydids, T is found by adding 161 to its mean number of chirps per